All right, the floor is all yours. Go for it.
Cool. So to introduce ourselves, we are the VEX Robotics High Stakes Skills Challenge Senior Design Team. I'm Nolan Paul, and I serve primarily on the design and build team.
I'm Nick Gilbertson, and I'm on the coding team.
My name is Matthew Carlos, and I was a part of the design team.
My name is Adina Lovato, and I spearheaded the coding team.
Matthew Williams, and I'm team lead. So first of all, what is VEXU? VEXU is a university-level robotics competition that is hosted around the world by the REC Foundation. And this year's game specifically is called High Stakes, where you can see in the pictures of the field layout, where the main objective is to score these rings that are spread around the entire field onto a combination of stakes like this mobile one here, and a few wall stakes and the one on top of the tower as well. And then at the end of the match, there's an additional endgame challenge to climb the middle tower as high as you can. You get more points the higher you are, obviously. Every year they release a game manual that outlines all the expectations of your robot and the constraints that it needs to fit within, which is used as a primary source for all of our decisions.
So the problem statement for this project originated from a problem. The MSOE VEX Robotics team doesn't have the necessary manpower to do the skills challenge on a yearly basis. That kind of limits the potential for the amount of points they can earn without qualifying for more tournaments, like Worlds, for example. So the objective for our team is to serve as that supplementary material and manpower. We're going to design and build a robot that can move the rings in an autonomous fashion that will complete the skills challenge as successfully as possible. And we're going to design, prototype, test, build, and iterate upon a robot and autonomous code for the entire year.
So for the background research, our primary source of the research was the game manual that VEXU releases every year. And the versions updates, we have to continuously go back to it and see if we're within the constraints and the rules. But we use this to see what our robot needs to be able to do and what we're allowed to do based on the situation. But due to the culture of VEX, most of our research had to be like videos based on the other groups and teams, mostly from the high school level, just like where we get inspiration from a robot. And not only us did this is just generally what we do in VEX. A lot of other teams also use videos for inspiration. And another source we had was C++ language tutorial, since we didn't know how to do C++ beforehand, but we needed to learn it so we could implement it with the team, since that's the coding language that they use. So this is just one video example that we use where we just like look at a mechanism from a robot, and we have plenty of videos we looked at. This just highlights one where it's just a claw mechanism where you just go to the ring, you pick it up. So it just demonstrates that specific mechanism. And there's other mechanisms like intake mechanisms, drive bases, so on, that we demonstrate. So in terms of the constraints that we got from the game manual, obviously you have to use motors that are supplied from VEX, as long as like the brain and the battery. You're only allowed to have one brain and battery on the robot, which is not a big constraint for us anyway. As well as things you're not allowed to do. You're not allowed to outsource any manufacturing or anything, since you have to do it all yourself. We manufactured a lot of our parts and 3D printed some of them as well. In terms of the tower, it's demonstrated there that there's three levels that we need to achieve. The fourth level is just to demonstrate you like can't skip levels, basically. And there's different planes. You can only occupy 2 planes at once, and you can't be within more than 3 levels at a time. So it's like you can't really skip a level. You have to achieve a level 1 climb, then a level 2, then a level 3. And that's just the vertical constraint of our robot. So in terms of the horizontal constraints, our robot can only be 15 inches by 15 inches. You can only expand in one horizontal direction at a time, which is different than our vertical constraint. So if we extend in one direction, in total we could extend another 9 inches because our robot's only 15 inches long. And if we tried to extend in multiple directions at once, we would be disqualified. That's an illegal move.
And with the design constraints out of the way, we kind of started looking at what we wanted the robot to achieve. So diving into our target specifications, we want the robot to achieve 77 out of a possible 110 points. This number was decided on based on a game analysis. As you can see, the point distribution kind of added up how many points we think is possible, and then came to that 77 number. For some like clarity, I guess the top teams in the world are scoring around 60 points currently. So we think we can get 77 and be the best in the world. To do this, we're going to need to load rings consistently in an average time of less than 2 seconds. Loading a ring is everything from intake all the way to depositing a ring onto the mobile goal. Additionally, we would like to achieve a level 3 climb, as that's worth 12 points, which is a large chunk of the 77 that we're looking to get. And additionally, all of the above must be done autonomously with a pre-written program.
Moving into design generation and concepts, we started with the drive base, and we look at three major designs for the drive base. First one being an X drive, which has 4 omni wheels, each at 45-degree angles on the corners of the robot, which allows for both forward, back, and side-to-side motion, in addition to speedy turns. Looking at a Mechan drive next, which is a very similar concept, allowing forward and back and side-to-side motion based on the vectoring of how you spin the motors and the wheels. And then finally, the tank drive, which is just simple 2 rows of wheels on either side of the robot, which does allow for like 0-point turn, similar to the others. However, is a little less maneuverable, but more consistent. Going into decision matrix of these designs, we first outlined some criteria. The major ones I want to point out are the speed and acceleration, which we rated high, as it is very important to be as fast as possible, as we are under a 60-second time limit. And then also consistency. Everything has to be done autonomously, which means that even small mess ups in certain parts of the path can expound over the time of the match. From our analysis, we found that X drive is the most highly weighted, mostly due to its very high consistency. But due to the large design time it takes to implement an X drive and the lack of support on the coding front, we decided to move with the tank drive, which scored nearly as well. However, is a little bit more durable and a lot more supported on the coding side.
Okay, so moving on to the mobile goal intake. The goal for this mechanism is to be able to take the mobile goals and secure them, and then angle them so that the robot can then put rings onto the stake. So the first mechanism that we have to do this is the single stage draw, where we just have one movement of a bar that will be able to pinch the base of the mobile goal and lift it up. The second method that we have was a forklift method, which you see on the right, and that essentially shoves a base plate underneath the mobile goal and lifts and tilts it up back into place. And the double stage draw in the middle kind of combines the two, where you have the single stage draw to secure it, but it doesn't tilt it just yet. That's the job of the second stage, which uses a forklift mechanism to lift the entire first stage and base plate up off the ground and into position. So when comparing these 3 designs, we found that control would be the most important aspect, since we need the top of the mobile goals to be securely in place so that the transfer can put the rings onto the stake consistently, as well as speed, which a lot of these scored fairly well on. And so for the jaw, the single stage jaw, it unfortunately does not have enough power to be able to secure the mobile goal in place. So that one's kind of out of the running. However, the second stage draw does do that a lot better. The forklift, unfortunately, is the base plate would require to be too large for the robot. So that was kind of put out of the running because of that. So the single stage draw for its control and its smaller size and how fast it can control the mobiles. Additionally, we need to be able to pick up rings from around the field. So these rings are kind of just laid around the field, all separated. So we need to be able to pick them up quickly and reliably. So the first method that we have to do this is the flex wheel bar on the left, which basically uses a bunch of flexible wheels and pinches it between the ground and the bar and pulls in the rings that way. We also have the wheel flap method in the middle, which has 2 wheels with flaps on it to be able to pinch the sides of the ring and pull it in. And unfortunately, the wheel flaps are not very reliable in the force that they apply to the sides of the rings. So having flex wheels instead of wheel flaps puts a lot more force and has a lot more grip on the ring that way. So it uses the same design, just with flex wheels instead of wheel flaps. So when considering these mechanisms, we found that, again, control is the highest factor, since it needs to be able to pick them up reliably. Since in the autonomous coding, we only have one chance to be able to pick up the ring. So In this category, the wheel flaps unfortunately did not do very well because they aren't very consistent with that grip. But the two flex wheel methods did a lot better in that regard. So when considering those two, we then have to consider the motor allotment. So the motors are a lot heavier, so they take up a lot of weight and a lot of space. And the horizontal flex wheels take two motors instead of the one motor that the flex wheel bar uses. So we went with the flex wheel bar for its control, its consistency, and its lighter weight.
The next critical mechanism when designing a robot such as this is the transfer mechanism. It allows us to take the ring from the intake mechanism to the mobile goal. So it's critical for scoring points and achieving our objectives. We came up with 3 designs. First was the belt and flap method, in which it would use the flap to catch the inside of the ring and draw it up the incline towards the mobile goal. Additionally, we came up with the double chain method, where it would be mirrored for symmetry, and the ring would sit upon 2 chains and would be drawn over to the mobile goal as well, in a similar manner. The final design was a flex wheel design, where we'd have a row of flex wheels on one side and a solid wall on the other, and use friction to roll the wheel up the incline and deposit it onto the mobile goal. Breaking down the weightings of this, speed and consistency were by far the most important criteria, as we needed to be very fast and very consistent so we can score rings and not lose any during the match. In this regard, the belt and the chain were not very consistent because it didn't have a way to hold the ring in place precisely, whereas the flex wheel chain or the flex wheel line did. That allows us to control the ring very precisely at its stage throughout the incline climb. So we went with the flex wheel transfer system because of its high weighting score, and more importantly, its consistency.
So the next mechanism we then intend to design here is the non-mobile goal objective mechanism, which essentially just takes the rings and places them on stakes that aren't the mobile goals, which are either the wall stake or the ladder stake. And we have 2 initial designs here, which are the spike mechanism and the claw mechanism. The claw mechanism was demonstrated from the one video we did in our background research, where it just picks up from the sides of the ring and places it onto the stakes. The spike mechanism, which is another idea we thought of, would grab from the middle of the ring and expand to pick it up, and then it would drop it on the stake as needed. So for weighting here, obviously we wanted to be really consistent and really fast. Both of these designs are pretty precise in like where you place the ring, so they're really consistent in that. But the claw mechanism is a lot slower because you have to use pneumatics to pick it up and place it on the ring throughout. So tentatively for now, we're going with the spike mechanism, but that's way later in the design process. These points are like harder to score, and it'll be later in the design process for us, and we'll add it to the robot later. So.
And then for the endgame mechanism, we came up with 4 ideas for this. The first of which was a double side pull-up. So in the double side pull-up, the robot will drive up to the ladder and then reach out with 2 arms and kind of pull itself up that way. The monkey pull-up does a similar thing. Instead of 2 arms reaching up at the same time, however, it alternates and climbs up with like a monkey bars. And then a whale tail is the 3rd idea we came up with. For this one, the robot will drive up in reverse and then kind of reach up and grab one of the rings from behind or one of the rungs from behind and able to pull itself up that way. And a single side pull-up is very similar to a double side pull-up. However, instead of 2 arms reaching up, it's a single arm. And then looking at the kind of decision matrix for this, we came up with some criteria that we wanted to meet. And then we rated speed, consistency, and stability the highest, as speed is important because we are under a time limit for the endgame. Consistency because we want to program this autonomously, so it has to be consistent throughout trials. And then stability because we don't want the robot to fall down mid-endgame and potentially damage the robot. So out of the 4 designs, monkey and whale tail were kind of ruled out fairly quick, as they didn't really stand out in any category. They weren't super durable. The double side pull-up and single side pull-up were definitely the 2 options that we're going to look forward in. But again, this mechanism is going to be one of the last things to design, because not only is it the last part of the like a single skills challenge, but it's also the last thing we design. So we're still deciding between the single side pull-up and double side pull-up.
Moving into the actual design of the robot, we used PTC Onshape to all of our CADing for this project. It's what the Radar Robotics team uses, and it also allows just great collaboration between team members who might be working on the same document at once. We started with the drive base, as it is kind of the base of what all robots are designed off of, as like all the other mechanisms have to be designed to fit into the drive base. To build it, we used a combination of CNC manufacturing to CNC all the side plates of the robot. In addition, we use a lot of 3D printing from everything from the gears to the brackets to the motor mounts and spacers and everything like that. One important part was the tolerances, because we want to make this as compact as possible, because we want to leave as much space for other mechanisms as we can. However, we also don't want to introduce any unwanted friction that would slow down the robot over the course of the match. Another thing is the odometry, as you can see in the middle there. So we have both forward, back, and side-to-side rotary encoders that track the position on the field, in addition to an inertial sensor, which is just kind of an accelerometer, which allows the robot to autonomously figure out where it is on the field at any given point, allowing for a lot higher accuracy in the autonomous motion.
And then speaking of the autonomous motion, the next thing we looked at was designing the autonomous portion. So the first thing in order to design this was looking at how we want the robots to maneuver around the field. As you can see on this diagram, Robot 2, there's two robots. Robot 2 is going to dominate the right side of the field, picking up all the rings and mobile goals, whereas Robot 1 is going to look at the left side of the field and do the same thing. For clarity, both of these robots are going to be on the field at the same time, both running in a completely autonomous mode. And these paths were chosen based on trigonometry, figuring out the shortest and most efficient way to get all of the things we need to get on either side of the court. Additionally, some factors we had to look at were that the rings are going to get intaked on the front of the robot, whereas the mobile goals are going to get intaked at the rear of the robot. So we had to figure out how we wanted to kind of swivel the robot in order to be the most efficient and pick up everything we needed to.
And as far as familiarizing ourselves with C++, unfortunately, no one on the team has had experience with C++, so we had to start from the beginning. So we gave ourselves about a month to learn all the basics of C++, including the syntax and formatting. So for example, C++ is not space, it doesn't require the spaces like MATLAB does. Instead, it has all this punctuation that we have to make sure is there in order for the lines of code to work properly.
And then moving into selecting a coding environment that we wanted to use. Pros and Easy Template was pretty much the only option for us, as that's what the Radar Robotics team uses. So if we had any like fatal errors in our code, we could look to them for assistance. Additionally, Pros and Easy Template is essentially built for VEXU, so it's kind of it was a no-brainer to go with Pros and Easy Template for our coding environment.
Unfortunately, there have been some issues with having Pros and Easy Template as our coding environment. For example, we had an issue with the brains updating, and that required the coding environment to be updated as well. However, Pros wouldn't want to update until Easy Template updates, and Easy Template doesn't want to update until Pros updates. So having a complex coding environment like that has some major downsides when it comes to updating. However, Easy Template does make things a lot easier to use. It simplifies the C++ syntax to be able to take large functions and be able to simplify it to a single line of code. And the only issue with that is that sometimes there are cases where it cannot simplify things like delimiters or headers. Those are things where we've had a lot of errors with, because it's something in C++ that's very complicated and cannot be simplified.
And then despite all of the errors that we did have with coding, we were able to get a drivetrain working. So as you can see here, this is Robot 2 driving along the field. It's going to the selected coordinates and essentially picking up the rings, or will once we get the mechanisms on. But so far, this is just the drive base. Additionally, with this, we did some PID tunings in order to ensure that accuracy and stability were incorporated into this design. In order to do the PID tuning, we kind of told the robot to go forward 2 feet, and if it went forward 2.1 feet, then we'd adjust the PID tuner until we got perfectly 2 feet. And that was done for both translational movement as well as rotational movement.
So this semester we set up to make a preliminary design and start the coding of a robot. We're able to write in a fully autonomous code capable of moving the drivetrain to various points around the field, as you just saw. In addition, code is written for other mechanisms that are soon to be added to the robot. In terms of design, we designed and built the drive base for the robot. In addition, that includes brain motors and odometry. Additionally, putting all the documentation not only for this team, but also adding documentation to the Radar Robotics Engineering Notebook, where in the most recent competition we went to, like 2 weeks ago, we were able to win the Excellence Award, which is the highest award that they give out, which qualified the team for World, which means that we will be able to showcase our skills in the World Championship later in May.
In addition to what we were looking at for this semester, we want to look ahead a little bit and figure out what we want to do for the World's tournament at the end of the day. We wanted to be responsible for designing the completely autonomous robot with driver control integration so that we can add to the posterity of the VEX robotics teams that they can use us for research purposes later on, should they want to improve on stuff. Additionally, we want to make a functioning prototype that meets all of our specifications and requirements so that we can compete in the skills challenge at Worlds. And finally, we want to make this all autonomously coded, so that's got to be iterated and optimized by Worlds in order to have the best chance at scoring the points that we wanted to score.
We're going to take this opportunity to open it up to Q&A from the panel and any other questions you guys might have.
Are you guys worried that using 3D printed gears and drivetrain and mechanisms will cause wear and inconsistencies over time?
We make sure to use 3D printed filament that is not just the cheapest stuff you can get. We do some thought and effort into the materials we're using. We use the PLA Plus for everything, and we've not had any issues with wear from the team for many years. So.
How did you guys go about speccing out the motors for the robot?
We are restricted in the motors. We have to choose the VEX motors. We can't really go outside of that for the specifications of the competition. They like their money and don't want you buying other people's motors.
Should you just give in the motors?
Yeah. They do have multiple types. They have 11 watt and 5.5 watt motors. But typically for the college level, when you're not restricted on how many motors you can use, using all 11 watt motors is typical.
So there's no consideration of the loading on the motor or anything like that?
We do have we do choose how many motors we want to use. Like for example, this drive base, I don't know if it's easy to see, has 6 motors on it. So choosing six motors in opposed to 8 or 4 that you can commonly see is just so we can get as much power and torque as we can on the wheels while also increasing speed. So the gear ratios were also considered. The motors are spinning at 600 RPM. We gear that down to 450 at the wheels, so we get the exact speed and the acceleration that we want. So it's easily controllable on the field, but also.
Did you have some targets that you wanted to hit in terms of acceleration per se?
Targets we wanted to hit somewhere around. This is kind of weird to think about, but the field is 12 foot by 12 foot. So we wanted to hit somewhere above 6 feet per second. So we want to cross the field in 2 seconds was kind of our goal.
So you did those calculations?
Yeah.
Did you achieve a high enough competency with your coding to do what you needed to be done, or is that still a challenge?
That is still a bit of a challenge. We haven't been able to test the coding, unfortunately, because of the errors that we've encountered along the way. However, the VEX Raiders robotics team does have a dedicated coding team with software engineers in there as well. So we've been able to ask them for help with learning the coding environment and learning the syntax to be able to help us along the way.
So you said you wanted to get 77 points, right? And top teams are getting 60. And then you were talking about your drivetrain. I think you selected the one that was second best, not the best option because of the coding. I guess my question is, one, why are you limiting yourself to 77 points, not the full 110? 2, could you not have gone with the better drivetrain and utilize the AI tools to learn coding and help you with the coding faster, right? Because this day and age, you don't have to learn all the syntax, right? You should be able to use those tools to kind of speed it up. Just kind of your thoughts on that.
We, in terms of design, the tank drive was selected because while we did our analysis based off of the skills challenge, when you're basically up against the clock, right? So you have 60 seconds to score as many points as possible. But the more common part of the competition is what the droid robotics team focuses on is the head-to-head competition. So, and in that competition, tank drive is really the only viable solution because of its durability. X drives don't have the power and they don't have the ability to compete with teams pushing them around the field or whatever. So using a tank drive, there's a lot more support for it in terms of, yes, coding, but also X drive didn't really, the advantages weren't so great. The only real advantage you get is the ability to strafe. And if you plan your autonomous correctly, that's not too big of a deal.
And to answer the other part of your question, in terms of the point scoring, we figured out like analytically the max we could get is 110, and most teams are getting the 60, but we figured we could get at least like 77. Our goal is to score higher. We want to be the best. So if other teams are improving, we seek to be better than that and improve our score a lot. At the moment, 77 is just like a goal for us to hit. And then once we achieve that, we want to surpass it and iterate to become better.
And then that 60 number, just to say, is what they're scoring now, not what they're going to score in 3 months from now when the competition comes.
And then could you guys talk about some of the math calculations, simulation analysis that you might have done in this part of the project?
So you can go back to the target specifications slide. So basically, like there's a specific amount of rings that are like set in a specific orientation throughout the field, and there's specific point scoring for each of them. There's 2 different colored rings. There's the red and the blue ones. We can only score the blue rings if they have like the red rings with them. So like there's a specific amount of red rings, and you can't score at all the blue rings because of that reason. But the climb, because there's 2 robots, that's like 12 points per robot on a level 3 climb will give us 24 total points there. If you have multiple rings on a stake, you'll score more points, but the top ring on the stake is 3 points. And if we get like the top ring on like the ladder, there's a specific stake up there that scores you 3 points up there. But each of the stakes, like putting all the rings on the stakes and on the mobile goals throughout it and achieving different climbs would score us the points.
The biggest thing is also time. We are limited to 60 seconds in how many points we can score. So doing even just scoring less than 2 seconds from intake to all the way out to the mobile goals only allots very minimal time at the end for being able to score the wall stakes or anything like that. So it's really a competition against the clock, and it's rarely ever seen that a team scores all points available to them in the skills challenge.
Yeah, that's why we like set priorities for ourselves, where it's like we want a level 3 climb because that's worth the most amount of points. Like mobile goals, when you place them in the corner and you score a lot of rings on them, that gives you also a lot of points, which is why we like weighted our design primarily towards like scoring mobile goals and rings on the low field rather than wall stakes and the top of the ladder.
There was point breakdowns.
Yeah,
And the trigonometry map too. We can explain that.
Yeah, I think Dr. Slaylock is interested in the math that was used to optimize your points and
Yeah, so if you kind of go to that slide, the autonomous one.
Yeah.
So we kind of calculated the distance between all of them and then added up, how like the complete distance. So if this distance is, square root 2 times 2 feet, then half a foot, kind of added all of those combinations up and chose the shortest distance one. And also, again, another consideration was intake rings from the front, intake the mobile goal from the rear. So we kind of incorporated that into those calculations as well by doing, okay, we want to intake this mobile goal from the rear, but this one we have to intake from the front. So we have to kind of swivel around and pick it up that way. So it was kind of just adding up all the distances and finding the most efficient route.
We also have to consider time with the 2 robots because they're working in tandem. If you notice on the right side of the tapping, you can see that some of the mobile goals are actually dropped by one robot and picked up by the other robots. So making sure that they're both in sync and that they're on time with each other ensures that the packing does work and they can work together to get the mobile goals where they need.
All right, yeah, I think I've already asked you all my questions in
Awesome.
previous presentations.
Yeah.
So, all right, if there's no other questions, well done.